Hello, wonderful audience. Thank you for choosing to spend your time with me. Thank you for joining us on this exploration of Bayesian-optimal mechanism. We hope you find it enlightening. A Bayesian-optimal mechanism (BOM) is a mechanism in which the designer does not know the valuations of the agents for whom the mechanism is designed, but the designer knows that they are random variables and knows the probability distribution of these variables. A typical application is a seller who wants to sell some items to potential buyers. The seller wants to price the items in a way that will maximize their profit. The optimal prices depend on the amount that each buyer is willing to pay for each item. The seller does not know these amounts, but assumes that they are drawn from a certain known probability distribution. The phrase Bayesian-optimal mechanism design has the following meaning. Bayesian means that we know the probability distribution from which the agent's valuations are drawn, in contrast to prior free mechanism design, which do not assume any prior probability distribution. Optimal means that we want to maximize the expected revenue of the auctioneer, where the expectation is over the randomness in the agent's valuations. Mechanism means that we want to design rules that define a truthful mechanism, in which each agent has an incentive to report their true value. As we move forward, let's uncover the untold stories and fascinating intricacies of example. There is one item for sale. There are two potential buyers. The valuation of each buyer is drawn IID from the uniform distribution on. The Vickrey auction is a truthful mechanism, and its expected profit, in this case, is the first price. Sealed bid auction is a non-truthful mechanism, and its expected profit is the same. This auction is not optimal. It is possible to get a better profit by setting a reservation price. The Vickrey auction with a reservation price of achieves an expected profit of, which in this case is optimal. In this chapter, we'll be shedding light on notation and its role in shaping our understanding. We assume that the agents have single-parameter utility functions, such as a single-item auction. Each agent I has a value Vi, which represents the agent's winning value E, the agent's valuation of the item. We do not know these values, but we do know that each Vi is drawn IID from a certain probability distribution. We denote by Fi the cumulative distribution function. F is P, and by Fi the probability distribution function. F is Fi's. An allocation is a vector X such that for every I, Xi is 1 if agent I wins and 0 otherwise. Each allocation might have a cost to the auctioneer, CAX. The surplus of an allocation is defined as Sex X IV ICAX. This is the total gain of the agents, minus the cost of the auctioneer. The surplus is the largest possible profit. If each winning agent I pays exactly their value Vi, then the profit of the auctioneer is exactly the surplus Sex. This means that the auctioneer takes all the surplus to themselves and leaves 0 utility to the agents. This maximal profit cannot be attained because if the auctioneer will try to charge each winning agent their value Vi, the agents will lie and report a lower value in order to pay less. The Bayesian mechanism comes to address this problem. In this section, we'll be deep diving into the Bayesian mechanism, unraveling its complexities and uncovering valuable insights. Roger Bayesian designed a Bayesian-optimal mechanism for single-parameter utility agents. The key trick in Bayesian's mechanism is to use virtual valuations. For every agent I, define its virtual valuation as WEVI equal VI if frac FEV if EV. I note that the virtual valuation is usually smaller than the actual valuation. It is even possible that the virtual valuation be negative while the actual valuation is positive. Define the virtual surplus of an allocation X as Sex XIW if ICAX. Note that the virtual surplus is usually smaller than the actual surplus. A key theorem of Bayesian says that the expected profit of any truthful mechanism is equal to its expected virtual surplus. The expectation is taken over the randomness in the agent's valuations. This theorem suggests the following mechanism. Ask each agent I to report their valuation Vi based on the answer and the known distribution functions Fi, compute Wi. Compute an allocation X that maximizes the virtual surplus X. To complete the description of the mechanism, we should specify the price that each winning agent has to pay. One way to calculate the price is to use the VCG mechanism on the virtual valuations WI. The VCG mechanism returns both an allocation that maximizes the virtual surplus and a price vector. Since the price vector corresponds to the virtual valuations, we must convert it back to the real valuation space. So the final step of the mechanism is take from each winning agent I the price PIWI up I, where PI is the price determined by the VCG mechanism. In this section, we'll be peeling back the layers of truthfulness to reveal its true essence. The Bayesian mechanism is truthful whenever the allocation rule satisfies the weak monotonicity property. The allocation function is weakly increasing in the agent's valuations. The VCG allocation rule is indeed weakly increasing in the valuations, but we use it with the virtual valuations rather than the real valuations. Hence, the Bayesian mechanism is truthful if the virtual valuations are weakly increasing in the real valuations. If for all I, WI is a weakly increasing function of VI. If WI is not a weakly increasing function of VI, then Bayesian ironing can be used. Bayesian's mechanism can be applied in various settings. Two examples are presented below. In this section, we'll be exploring single-item auction. Suppose we want to sell a single item, and we know that the valuations of all agents come from the same probability distribution, with functions f. Then, all bidders have the same virtual valuation function, W. Suppose that this function is weakly increasing. In this case, the VCG mechanism reduces to the victory auction. It allocates the item to the agent with the largest valuation highest bid. But Bayesian's mechanism uses VCG with the virtual valuations, which may be negative. Hence, Bayesian's mechanism, in this case, reduces to victory auction with reservation price. It allocates the item to the agent with the largest valuation, but only if its virtual valuation is at least 0. This means that the reservation price of Bayesian's mechanism is exactly W. So, if we know the probability distribution functions f, we can calculate the function W, and from it, find the optimal reservation price. Get ready for an exciting exploration as we unravel the mysteries of digital goods auction. In a digital goods auction, we have an unlimited supply of identical items. Each agent wants at most one item. The valuations of the agents to the item come from the same probability distribution, with functions f, and virtual valuation function W. The VCG mechanism allocates an item to each agent with non-negative virtual valuation, and charges the minimum winning price, which is W. This exactly equals the optimal sale price, the price that maximizes the expected value of the seller's profit, given the distribution of valuations. Argmax once. Moving on to the next segment, we have alternatives. Bayesian-optimal mechanism design requires knowing the distributions from which agents' valuations are drawn. This requirement is not always feasible. There are some other alternatives when the distribution is not known. A prior independent mechanism can be used. When it cannot even be assumed that the agents are drawn from some probability distribution, a prior free mechanism should be used. Thank you for watching. I appreciate your support and I'll see you in the next video.